In this video, we will talk about the zeroth and first laws of thermodynamics, as well as defining what we mean by heat, work, and enthalpy. The zeroth law of thermodynamics was actually the fourth law to be developed, but because it is foundational to the other three, it got the title zeroth law, so that it would come before the first law of thermodynamics. The zeroth law states that if object A is in thermal equilibrium with object B and object B is in thermal equilibrium with object C, then object C is in thermal equilibrium with A. This is the classic if A is equal to B and B is equal to C, then C and A are equal to each other. The reason why this is foundational to our discussions of thermodynamics is this actually is what we use to describe how a thermometer works. So if we take object B as being our thermometer and touch it to object A, and it reads a particular value, and we then take that thermometer and touch it to C and it reads the exact same value, then we know that A and C are in thermal equilibrium with each other. The first law of thermodynamics was initially stated by Rudolf Clausius in about 1850. Again, as a reminder, the study of thermodynamics was initially performed by engineers who were interested in maximizing the efficiency of the steam engine, which was developed around this time. So the original statement given by Rudolf Clausius was that in all cases in which work is produced by the agency of heat, a quantity of heat is consumed which is proportional to the work done, and conversely, by the expenditure of an equal quantity of work, an equal quantity of heat is produced. In a thermodynamic process involving a closed system, the increment in the internal energy is equal to the difference between the heat accumulated by the system and the work done by it. Okay, so essentially what this is saying in the first case is if you pull some heat to do some work, the values are going to be the same. If you're using some thermal energy to do some work, as they were doing with steam engines, the maximum amount of work that you can do is equal to the amount of heat that was consumed. Conversely, you can get things to heat up by applying work to them, and the maximum amount of heat that can be produced from work is equal to the amount of work that you did, where work and heat are mechanisms of energy transfer that we will describe in greater depth in our next slide. The second statement is essentially what we will be using for our statement for the first law of thermodynamics, which is the internal energy of an isolated system is constant. Another working definition would be that energy can neither be created nor destroyed. So the internal energy of a system is equal to the amount of heat given to the system and the amount of work done on the system, right? So essentially, these all boil down to you can't get energy from nowhere. It has to come from somewhere. So energy itself can neither be created nor destroyed. It has to come either from the system or from the surroundings. And if we isolate something, then the amount of energy in that isolated system is constant. We can either have it do work or have it do heat, but if we're using some thermal energy to do some work, then the amount of heat energy or the temperature of our system will necessarily go down in our effort to do work. So mathematically, the change in the internal energy of a system is equal to the amount of heat given to the system and the amount of work done on the system. The classic equation for this is delta U is equal to Q plus W. The Tro textbook uses delta E instead of delta U, but depending on where you look on the internet, you will see either delta U, which it will be much more common, or delta E. The delta E is change in energy. U is what gets used in the study of thermodynamics for internal energy. So what this is saying is that the internal energy, or the change in internal energy, is equal to the amount of heat that is transferred plus the amount of work that is done. So the internal energy of a system increases if heat or work energy are provided to the system. We will be using the convention of a plus sign to indicate that the energy is going into the system. So if thermal energy flows into the system, the value for Q will be a positive value. Similarly, for work, if the work is being done on the system, then the sign for W will be positive. Now, work itself can come in many different forms. We can either talk about expansion or compression, primarily for gases, electrical energy, and then one that you might be familiar with from physics, gravitational and mechanical. Our electrical energy we will talk about when we get into electrochemistry. In terms of expansion and compression, that is the one we will be primarily interested in for the discussion in this set of videos. Now, what heat and work look like on the atomic scale is what differentiates them. Heat is the transfer of energy via a disorderly motion of atoms. So if we think about heating something up, you can imagine putting a Bunsen burner or some sort of heat source onto the side of a container. What happens is that thermal energy gets the molecules in the container to start jostling around and moving in random directions. If you have gas molecules that are inside the container, they will come into contact with the side of the container, which is now moving more violently, but that motion is in random directions. So when the gas molecule comes into contact with a wall, it is being hit by the wall, but the direction of the atoms in the wall, they're moving in random directions. So they will send the gas molecules flying off with extra energy in a random direction that contains essentially an arc of 180 degrees. So they can go off in any random direction away from the wall with that added energy from the molecules in the side of the container jostling around. Work energy, on the other hand, is transferred energy via an orderly or organized motion. If we think of the movement of a piston or electrons in electric current, what we envision, if let's say we're looking at a piston, is we have our container with gas molecules. The piston itself, or the wall of the container, is moving in one direction. So every single gas molecule that collides with the wall of the container is being given extra energy in a very organized direction, right? If the wall of the container is moving up, then every single gas molecule is being given added energy in the up direction. Now, after those gas molecules move in the up direction, they will collide with other molecules that might have bounced off the top of the container, and over time there will be no net direction to the energy, because if you have an atom coming down from the top, it will collide with one of these gas molecules and they'll both go off in random directions. So through random collision, this organized motion that it was initially coming from the wall of the container moving up in a particular direction gets converted to random disorderly motion that is the exact same motion as you get from thermal energy being transferred. What this means is that when the wall is done moving, you will not be able to tell by looking at the atoms whether the energy was transferred thermally or via work. In fact, if you ever try to inflate a bicycle tire using a bike pump, if you do it very, very quickly and violently, what you will find is that the bike tire actually heats up. The reason that you would have to do it quickly is the heat energy does dissipate from the walls of the tire. They are not good insulators. So if you're pumping up a bike tire and you do it fairly quickly, and then you put your hand on the bike tire, you'll notice that it will feel hot or warm. And that's because the orderly motion of the piston moving down as you're pushing the bike pump causes the gas molecules that you're pushing into the tire to go in a particular direction. When they get into the tire, they bounce around off the sides of the walls of the tire and they start having disorderly motion, which looks the exact same as thermal energy. And so inside the tire, it looks the same as if you were to take the gas that was in the tire and probably not put it under a Bunsen burner, but heat it up some other means, right? So it feels hot because it has what appears to be thermal energy, right? And thermal energy or temperature is a measure of the kinetic energy or the average kinetic energy of the gas molecules in your container. So if you're supplying them with work, you're giving them kinetic energy. They then jostle around and shift the directionality to be in random directions through collisions, and so it looks the exact same way as if you supplied that kinetic energy through a thermal means by heating. Now the last concept for this video is going to be enthalpy. Now heat and work are path dependent. It matters how you supply the work and it matters how you are doing the heating. Enthalpy is what we're going to use to decouple our heat from a particular path. And it's done by defining the path. So enthalpy is defined as the amount of energy exchanged under constant pressure conditions. So if we're keeping the pressure constant, there is only a limited way of doing work that is under constant pressure. And so we are, in essence, defining the path for our particular system. So the reason why we care about enthalpy is constant pressure conditions are similar to those that you would do in a lab, right? So if you have a beaker, beakers don't really have a change in pressure, right? The top of the beaker is open, and so the pressure being exerted onto the surface of your liquid or your reaction, whatever you're doing, is going to be the pressure of the atmosphere around you. And so that value will remain fairly constant. So the enthalpy of a reaction is the amount of thermal energy either given off or absorbed by the reaction or process. An example of one of these types of processes is a phase change in going from like a solid to a liquid, solid to gas, gas to liquid, liquid to gas, some sort of a phase change. Now, enthalpy itself is a state function. We are defining it as the difference in energy between where we start and where we end. Because it's defined as the difference in energy between where we start and where we end, it doesn't matter the path that you take to get there. You could take this particular path here, or you could take another path that goes here, there, or you could take a path that goes up much higher, comes down much lower. It doesn't matter. All that matters is the difference in height between where you start and where you stop. So state functions are properties whose value depend only on your initial and your final condition. So where you start and where you end, not the path taken between them. Work and heat, the amount of work that you do does depend on the pressure and how much you're changing the volumes. So both heat and work are path dependent, but enthalpy is path independent. And we can use this, and we will use it later when we're talking about driving forces for reactions and how much useful energy we can get out of a particular reaction system.